Hello, welcome to part 2 of my Utilizing Data Models video series. We're going to talk about physical data models. Quite simply, this is what you're going to build. You're going to build something physical within your workflows or within your ETL tool of choice, and you're going to end up with a new set of data that you'll be using for future reporting purposes or for other storage and access, and that is what is physically going to be out there. What we're going to look at is talking about a relational model, a dimensional data model, a reporting table data model, which is what most of you will be generating, and I just want to point out the differences and why you might want to be aiming for something slightly different. And then, of course, we'll talk about the living physical data model, just as we talked briefly about a living logical data model. I covered this topic in the logical modeling, but it applies to the physical as well. Why do you want to model your data? Well, we take it from the construction industry and the fact that we have some views of what we are doing. We plan what we are doing. We share what we are doing with other people, and everybody has a shared vision of what we're going to do. And a data model is part of that vision. It also makes your life easier as you're trying to make decisions doing ETL or other data analysis or your extraction and blending and cleansing of data to know where it is that you are heading, and you can have that in mind. So what is a physical data model? Well, it's a visual representation of what you are going to be building, and it typically derives from the logical data model, which is why we talked about the logical data model first. And if you keep that logical data model in mind, and if you generated that originally, it makes your physical modeling a bit easier. The nice thing about going from your logical data model to your physical data model is that you can choose what kind of physical data model to implement independent of the logical data model that I typically build. And as a side note, you can also use a data model and model your NoSQL structures depending upon what kind of tool you're using, as well as where it is that you see that you're going. So some people say, well, I'm not building a database. Why do I need to model it? Well, you can model the physical side of any type of data store that you need to implement. And quite briefly, what is a physical data model? It is simply a blueprint that you've laid down in front of yourself that you'll be following through the implementation process. It's a guiding light as well as a discussion point. So we're going to be building three different physical data models from our Puppy Performance logical model. And if you remember from the previous session, this is what we ended up when we were finished with our logical model. We had some entities and the relationships between those entities that we will want to implement within our physical models. So what is a relational data model? You've probably heard this term a number of times. One person once said, well, relational data model is what I store inside of a relational database. And the answer is not quite. You can store pretty much anything you want in a relational database system, but it'd be nice if you actually build a relational model. Relational models adhere to the rules of normalization. They've been around since the 70s, if not before the 70s, and it is what we like to think of as the golden image of what we will be building as far as the data architecture and database people in general. Why are rules of normalization important? It's because if you follow them, you build yourself a very efficient and extensible and performant data store. Again, I've always said many times, if you're building a very small set of tables, you don't really have to build them normalized because they will be performant as well. They might not be extensible, but they will be performant. And once you begin to build larger and larger data sets, then you'll begin to notice the pain of not having normalized your data. There are a couple of types of tables, and we'll be looking at these through our development process. You have parent tables, the top of the relational model. You have children table, which are related to parent tables. You also have lookup tables where you have reference data that you will be utilizing to better explain your data. And then you also have cross-reference tables, which goes ahead and joins to either parent tables or two child tables together in such a fashion that you have the ability to expand out your data set. And we'll be looking at these through the modeling of our puppy performance in a relational sense. So what we're going to do within this context is use my sqlDBM to build this relational data model. I'm not going to walk you through all the ins and outs and all the details of this because that would take quite a period of time, but instead I'll just simply show you the steps that I've done along the way. So if you take a look at the logical model, what you see in the top of all this as far as a parent table is concerned is that we have the kennel. And we'll go ahead and we'll drop the kennel into our data model. I've already created the kennel. The kennel has an ID, a name, an owner, and an address associated with it. And as we looked at our logical model, we know that the kennel owns a puppy. And so the puppy table becomes the kennel's child. We put this here, and you see that because I've already built this, it went ahead and put into it the relationship between the kennel and the puppy. This is a relational construct that shows that the kennel has ownership or passes down identity into the puppy table, and we can see from this that the kennel ID has come down here. So this shows me that the kennel owns puppies. When we talk about reference data, we have another one to drop into here, and that is where we have a breed. Breed doesn't really own a puppy, but the breed essentially adds categorization or information to the puppy table. And so we drag the breed table into here and we see that it has the same type of relationship to the puppy as the kennel, but the slight difference in reasoning is that the breed doesn't really own something. The breed exists within itself, but it just simply helps categorize the puppy table so it becomes a reference table. Continuing to flush this out, don't forget that we have some additional pieces of information. We have, for example, the costume table, and then we also have the trick table. And as we drop these down here, we see that there is a relationship between the costume table and the puppy table and the trick table and the puppy table, but these occur in a many-to-many relationship so that the puppy has multiple costumes. The costumes belong to multiple puppies, but the relationship is not a one-to-one or a direct ownership or a reference data because a costume does not own, is not a parent to puppy, nor does it further define the puppy, and instead they have a more complex relationship, and this is the cross-reference table that we've been talking about. And simply when the puppy does a performance, that is when all of this comes together. So we go ahead and drop the puppy performance table into here, and we see that at the time of performance, all of these tables come together in a cross-reference or a many-to-many relationship to where the puppy, through the performance, and a costume and tricks through the performance have a relationship that can be repeated many times. The puppy may have that costume or that trick performed many times through different performances, and so we have the performance table with its ID. It has within it the costume, the puppy, and the trick, as well as some additional information such as the date of the performance and how long the performance went on. And the costume and trick tables basically are reference data, and they simply have a name and a description associated with them. So very simply, this is how we have generated a fully relational, normalized structure to contain our puppy information. One of the reasons why people do not like this kind of relationship and this kind of data model is it becomes a bit of work in order to feed each of these individual tables, possibly from a single data feed or from multiple data feeds. But this gives you the most flexibility, the most information, the most extensibility, and when data sets get large, this is a very easy way to store and access the data that you need. So going back to our presentation, This is a picture of the model that we just created that shows the relationships between the tables and our ability to store, populate, and access that data in a very efficient manner. We would implement this in the database as separate tables, and if we have a good modeling tool, it will generate the SQL for us in order to create these tables. On the other hand, if you're using a good ETL tool such as Alteryx, simply the output structures of those tools would create the table if you ask it to, and they understand the different databases that you might be using. Moving on to our next type of physical model that we would generate in order to build a set of tables, and that would be the dimensional data model. This is a term that has come around to talk about storing information in a more readily reportable fashion in data warehouses. Data warehouses provide you with two opportunities. One is it's a way to consolidate data across multiple databases, and two, it gives you structure that makes reporting easier, and a lot of the reporting tools that you use really do a good job of ingesting a dimensional model and giving you flexibility and performance when accessing that. Kimball was the first person to come up with or to actually define the dimensional data model, and is a big proponent of going and building your data warehouses along the lines of this physical modeling structures. There are other adherents to different types of data models for data warehousing, but they also usually all fall into the relational structures that we talked about previously. So what we're going to do is move away from the strictly relational and talk about the dimensional, but keep in mind that a dimensional data model is a type of relational database. It just has different table types as well as different relationships between those. Some of the table types that we'll be talking about within the dimensional data model are dimension tables. Some of the terms you'll hear that we'll talk about are conformed dimensions, degenerate dimensions. We'll be showing examples of both of these types of dimensions within our data model. We have junk dimensions, which is sort of a general term saying we're not exactly sure what it is, but we allow you to build it anyway. And we'll also be building a slowly changing dimension. This is where you can capture the change in data over time, so you can not only report as is, but you can also report as was. Within the dimensional data model, we also have fact tables. These are where your metrics are stored that you do your baseline reporting from. You have transactional facts that are individual facts associated with a transactions from the source system. You have periodic facts, which are the summarization of those facts reported at a certain period of time. For example, you might have a roll-up or a summarization of your transactional facts into a monthly fact or monthly periodic fact, or into quarterly or yearly, so that you don't have to do those within the reporting tool. They are done rather inside of the database. You have accumulating facts, which are facts that change and add additional value over time. And then we have what I like to call the factless fact table, and that is simply where dimensions come together into a fact table, but there is no metric measuring that. We simply have an existence. And finally, there are other types of table that Kimball had to allow us to build in order to continue through. Bridge table is a table that combines dimensions together. If you have a relationship to where dimensions are related to each other and that relationship is important to your data. Some of the bridge tables that you might want to build are things like in the healthcare industry, to where you have a dimension of patient and a dimension of diagnosis, and any patient at any point in time has multiple diagnoses. So you have a relationship that has to be built between them, and that would be a bridge table. You have hierarchical tables. Check some of my videos about building hierarchies. Hierarchies are a bit tougher to use within the dimensional model, and as well as they are hard to build. And there's ways to do that in dimensional model. We will not be talking about those today. And we also have a construct which I call a temporal table, which shows you change in information, either factor or dimension over time, that is outside of the slowly changing dimensions. I tend to treat that as a status. For example, if you have an order and an order goes through multiple statuses along the way, then the status change would need to be captured so that you can see when that status change occurs and over what period of time a certain order has a certain status. So let's go ahead and build our dimensional data model. And again, we can use our relational tool. What I'm going to do here very quickly is go ahead and create another diagram inside of this work in progress. We'll call this dimension. Let's call data warehouse be something simple. And again, I'm simply going to drag in the objects that I've already built for this so you can see how that is that they fit together. Now keep in mind, we're going to have a lot more tables, a lot more relationships, which is a reason why people don't like building them, because it is a bit more work to build those, as well as some things have to go on behind the scenes in certain situations. But if the conditions apply to what you need to do, you have a very complex source of data and or complex reporting needs, the dimensional model is what gives the extensibility and the performance that you would need for those types of data sets. And we sort of build this the same way we built before. We start out with a kennel. In this case, we have a kennel dimension. Now, when I build data warehouses, I tend to give my unique ID associated with the dimension, calling it WID or warehouse ID. This is useful because if you're bringing data from multiple sources, you might have conflicting IDs. So if the two source systems that maintain kennels for you all begin numbering at 1, they will have either conflicting or non-unique IDs for kennels or different kennels or for the same kennel. And then the data warehouse, this is where you need to go ahead and straighten all that out so that you do indeed have a unique ID for each kennel regardless of where it came from. And again, this point of this exercise today is not to show you how to build these structures, but simply to show you what these structures look like. If you have any concerns or needs for how to build any of these structures, please go ahead and subscribe to my channel, drop me a comment, and we can always cover some of the best practices for building your dimensional data warehouse or your relational data store in subsequent videos. But in this case, you see what we simply brought in is our kennel. We have the warehouse ID. We have information associated with it. We also change this not into a conformed dimension, but this is a slowly changing dimension as well, because the name of the kennel, the owner, or the address might change over time for this kennel, and we want to know when this specific record was applicable. So now we have, for this kennel name, we have an effective date for when this was the details for the kennel starting and ending. Let's go ahead and quickly drop in puppy in here, and you see that we have a much smaller, much more reduced puppy table, in this case a puppy dimension. This is a conformed dimension, which means that all the sources come together and it can be used across all of the data warehousing that we use. So this conformed dimension has the warehouse ID and the puppy name. All the other information that was in the puppy table and then in the feed will go into other places within our data warehouse, because this is the only piece of information that characterizes or further defines the puppy. In Data Warehouse, check out one of my presentations on the usage of an effective date dimension. Date dimensions are very useful for you to use, but in any reporting, because it gives you additional information that you don't have to look up. So whenever I build a data warehouse, I always build a date dimension. This is a sort of smaller date dimension than I typically create, but we have it here as well. As we bring in our other conformed dimensions, we've got kennel, we need our breed dimension, we need our trick dimension. So these are all the pieces of information that are used to characterize any fact that we would want to use in the performance. And I forgot our costume dimension. So these are our other conformed dimensions that we have out there. This gives us information about a breed that we can associate with any fact, a trick that we can associate with any fact, and we can use it across multiple sources. So we have our conformed dimensions, we have our slowly changing dimension. Now we need what we call the degenerate dimension, and that happens to be our puppy performance dimension. Here's our performance dimension. If you notice, there is no information that we have that further defines the performance. We had within the table, we had the performance date, but that will be satisfied by our date dimension. We also have the performance duration, but that's our metrics, which will go into our fact table. So essentially all that we have is a placeholder that allows us to build queries based upon the performance ID should we need it. So a lot of times you don't actually build this dimension, but I like to build it anyway just so it's sitting there in case we do find other characterizations or descriptions associated with performance dimension. So these are all the dimensions. These are all the entities that exist within our performance. That will help us categorize, sort, and access our performance. And we talked about the fact that this is our performance fact table. It has a relationship to every one of our dimensions. And it has our metric, which is the duration. So now whenever we want to find a piece of information or a metric associated with a performance, we can come in through any of these dimensions to find all of the performances by kennel, all the performances by customer warehouse ID, costume, and generate reports associated with those, rolled up by those, etc. And as you can see then, when we bring in our data feed, we'll populate the dimension tables and then finally populate our fact table and giving it the relationships to each of the dimensions that are out there. From your query standpoint, this tends to be a bit tougher to generate the query, but when you're dealing with a tool such as Alteryx or other your blending tools or any reporting tools, you're simply dragging and dropping things onto it. If they're intelligent enough, they can see the relationships in the database that you've created, and will be very easy for you to do drag and drop to bring in just the piece of information that you want. So what we talk about is the fact that I don't need all of this data for my report. If I'm only concerned about tricks and costumes, then I can just bring in these 3 tables and not all the tables carrying along that extra resources that go. So that is my dimensional model that fits in a data warehouse. It is very easy for reporting and it's very easy to extend and use going across other pieces of information. And typically this single dimensional model that has one fact surrounded by its dimensions is called a data mart. So this would be my puppy performance data mart. I might have many data marts out there that have different fact tables, but they share the conformed dimensions that I've used in this one physical model, so I don't have to rebuild or remodel those going forward. I can simply reuse those. So finally, let's talk about a reporting table data model. Very simply, this is denormalized. I'm simply going to build one table that has everything in it. It doesn't have any of the IDs. It simply allows me to go in and report this piece of information. It puts the onus on the reporting tool to be able to sort through and to clean up. It has a lot of redundant data potentially in it. It is also harder to maintain and moving forward. And very simply, this is one single table. And there is absolutely no reason that you should not do this in moving forward with what you're doing. Make it as big so you can see it. So simply for my puppy performance reporting table, I brought all this data together. It essentially was in one single feed. I put in the puppy ID and performance ID in order to create uniqueness. I don't really need to do that outside of this, because here are the pieces of information that I will be using in my reporting, which is the name of the breed, the customer, so the costume name, the kennel name. So all these are the pieces of information that came in from my feed. I put them into one table, keeping just the IDs necessary to make it unique so I can query into uniqueness. I have to assume that breed names are unique as well coming in, etc. And so this gives me ability simply to report this out as one single table. I've done all the work inside of my ETL tool to pull this together, hopefully to cleanse this up a little bit without the help of any relational structures. I might have a little bit more work to do, but you can see that this actually just gives me the data. So you're probably asking yourselves why the first two models when the third model does the job. Well, the answer is that this information makes it a little bit harder to sort forward, a little bit harder to share with other resources. This simply also limits me to what I can report about and how I can report it, because this is all the data that I have. And again, this is not a trying to say don't do this. It's just that this is the most rigid of the structures that you can build. But again, I model it by building a table within my data modeling structures, put the attributes in there, give them attributes, lengths, and names and types, and then I would physically create this table using the modeling tool to generate the SQL for me, and then I would populate it as well. So again, I have still done my data modeling. I have still put a blueprint out there. It's just a much simpler version that allows me simply to do the job at hand without having to extend out of it. And also what this doesn't give me, if you look back at it, it doesn't give me any reference to mapping this if the data comes from different sources. How do I build this from different sources of data? It's up to me to figure out while I'm doing my development, whereas something like the relational model that's being built would show me that where the data is coming from if all that data is not available to me within this structure. So here's my denormalized structure, does just reporting. And the final note is to keep your physical model alive. We've talked about this with the logical models, is that as you change what you're doing within your development work, if you've changed the attribute names, the attribute types, added certain attributes, taken away certain attributes, added a new relationship or a new table into it, update your physical model so it matches what you've learned while you're doing development. Again, it's a blueprint for what you plan to do. And if you keep it alive, it will show what you've done. It becomes an artifact for your documentation and allows you to move forward and refer back to it and update it along the way. I thank you for listening. I hope you subscribe. Drop me some comments about what else you'd like to see. If you'd like some more information on best practices for building the data behind any of these types of structures, drop the comment and I can look at doing that for within some of my future videos. Have a great day.